Okay, I know your heads are probably spinning. You're thinking, how can you possibly calculate the probability of the data on a complex tree? Well, the answer is you break it down into individual nucleotides. It's not that difficult. Let's talk about this particular example in which you have a figure a little lower on the document. You should look at the figure and compare it to what I'm talking about. So here we have 4 taxa in panel A. The first nucleotide is the letter C in all 4 taxa. And then we get to site J and we have CCAG. Now it's not that difficult to calculate the probability of these nucleotides on those 4 taxa. What we're going to do is take an unrooted tree with the 4 taxa and grab it anywhere. We can root it any place arbitrarily. Let's root it right here. Imagine this unrooted tree is made of wet spaghetti, and we can just pull this node to the root. That's what we have here. See, if we root it here, then 1 and 2 are sister taxa, just as they are here, 1 and 2. And 1 and 2 have C's. We have a new node, 5, and a root node, 6. And then taxa 3 and 4 are A and G, as we have at site J here. Let's calculate the probability of this series of events with likelihood. Now, one of the really cool things about likelihood is that it's going to calculate the probability of every possible state at all of the nodes. It's mathematically complex, which is why we need computers to do it. But computers are up to the job. So let's imagine we have our tree and we have our unknown nodes 5 and 6 here. This is going to be on panel D in your figure. We could assume that 5 was an A. Is it possible that 5 was an A? Well, yeah. Even if the taxa here are C's, there's some non-zero possibility that node 5 contained an A. And then on a branch length this long, the A changed to a C. And on a branch length this long, the A changed to a C again. Not likely, but possible. And then let's calculate the possibility that the root node was an A, stayed an A on a branch length this long, and then changed to a C. And then on a branch this long, stayed an A, and here stayed an A until it changed to a G here. Okay? That's a probability that we can calculate, given that we have a model for substitution rates across these branch lengths. Okay, so that's the probability of having an A here and an A here and observing these states in our terminal taxa. To this probability, we have to add the probability of starting with an A here, changing to a C along this branch, and then staying C along 2 branches this long. Now that's more probable than this one. And in fact, this distribution at the root and node 5 is one of the more likely of the possibilities. But the thing is, all of the possibilities are calculated according to our model. Finally, after we've done all 16 possibilities, AA, AC, AG, AT, CA, CC, and so on, we get to a T at the root node and a T at node 5. What's the probability of that, given our substitution models? So what we're going to do at site J is calculate the probability of every possible nucleotide state at each of the undetermined nodes. Now let's look at panel E. Panel E just summarizes that the likelihood of the entire tree is the product of all of the likelihoods together, each of the individual site likelihoods together. So the likelihood at site 1 multiplied by the likelihood at site 2 multiplied by the likelihood at site J all the way to site N. And we have then from 1 to N the product of all of the individual site likelihoods. That's an extremely small number. I mean, can you imagine how small that is? It's too small for us to even think about. But there's still a difference between a very tiny number and a very tiny number that's a little bit tinier. Okay, so we're calculating very small probabilities. And in order to get our heads around this with some value that we can actually think about, we use the natural logs of those likelihoods. So that likelihood values are presented in natural logs. So in order to get the likelihood for natural logs, we're going to add together all of the natural logs. So the at site 1 times site 2, or plus site 2, and then from 1 to n, the sum of all natural logs is our actual likelihood score. So in likelihood, the larger the value, the more likely an event is. This is different than in parsimony, where the shortest tree is the best tree. In likelihood, the most likely turn of events that created the data is the best tree.